Welcome you all. My topic of the research is experimental investigation on novel intake manifold design and polyamide glass fiber as alternate material for air intake manifold in single and multi-cylinder compressor ignition engine with diesel and biodiesel as fuels. My name is P.Arjunraj. This is the overview of my presentation. I'll be giving an overview about introduction, literature review, objectives and methodologies of the research, materials and methods, experimental setups and testing procedures, results and discussion, conclusion, future work, references, and list of publications. Let us go to introduction. The efficiency improvement of diesel engine is tremendous importance since they are being used across the globe. The most important component of diesel engine is cylinder, in which the method of fuel compression at higher temperature, that is the air and fuel blend is going to happen with high exposure. You know that diesel engine is working on the model of thermodynamic cycle, which is nothing but a diesel cycle for the burning out of fuel, where the air fuel mixture is burned at high temperature and pressure. You know that air intake manifold is shortly called as AIM. It is one of the important portion of the engine for the section of air into the engine. And also the distribution of the air is evenly going to take place at every intake port of the cylinder head. And this is the important function of the air intake manifold. And also, you know that volumetric efficiency has the impact on the size and shape of the air intake manifold. Intake manifold is a part of the engine that supplies the fuel air mixture to the cylinder. The primary function of the intake manifold is to evenly distribute the combustion mixture or just air in the direct injection engine to each intake port in the cylinder head, supplying an adequate quantity of oxygen to confirm the complete combustion. Controlling the temperature and pressure of the charge is important requirement for the air intake manifold, and also the impacting the bulk motion and also the kinetic energy to the charge for supporting and also for the mixing. You know that the air intake manifold has to provide as much as air as possible for its given volume. Engine efficiency is also affected by the air intake manifold design. Air intake manifold improves the performance of the engine by providing sufficient air volume to the combustion chamber. The size, shape, material manufacturing are the parameters to be studied to get higher air intake. Even distribution is important to optimize the efficiency and performance of the engine. The thermal conductivity of the intake manifold material shows a vital character in the engine performance, since it also increases the temperature of the intake manifold. When the temperature of the manifold declines, it increases the density, and turn the volumetric efficiency increases. The design and orientation of the intake manifold is a major factor in the efficiency of one engine. Let us go to the literature review. So these are some of the literature review that I have collected related to design manufacturing. These are all the title of the paper, and I have identified some of the problems and also the methodology used, and some of the results also have been identified. Design of air intake manifold has significant effect on engine performance, and the methodology used for this problem is spiral intake manifold has been used, and the result is volumetric efficiency of the engine was enhanced at varying load. Second problem I have identified is during intake manifold design, the volumetric efficiency is lowered, and also the power and output is also getting affected. The methodology used here is different geometries of intake manifold are used, and the result here is new intake manifold geometry was proposed to improve the volumetric efficiency of the engine by 6% at 3,500 RPM, consequently the increasing the indicator power by 3.68 kilowatt, which is nothing but 4.93 horsepower. And the third problem identified here in this literature review in this paper is the intake manifold considerably affects the power and volumetric efficiency of CA engine. And the methodology used here is intake manifold of CA engine is modified and it is manufactured by additive manufacturing technique. And the result here is for all load units, the volumetric efficiency, brake power, and brake thermal efficiency were considerably improved. The brake specific fuel consumption was also reduced. Now, the fourth research paper, in the fourth research paper, the problem identified are the exhaust emissions from car engines are high. At the same time, new technology are in demand. And the methodology used here is the inlet manifold design. And the result here is reduced fuel consumption, enhanced engine performance, and emission control. And the fifth paper indicates some problem which is related to the quality of the manifold, which has a direct impact on the performance of the engine. And the methodology used in this paper is designing a new three-dimensional cavity model of the intake manifold. And the result of this research paper is that improvement of power and economy of the engine. And in the development of plastic intake manifold title of paper, the problem identified was manufacturing the air intake manifold. And the methodology used here is blown injection molding. And the result here is new plastic intake manifold on supercharged 0.66 liter engine in the domestic market. And the other problems that were identified includes assessing the thermoplastic material like BA6 glass fiber 30 and PL6 glass fiber 35 percentage, and to find some of the optimized intake manifold. And B20 biodiesel blend is on par with diesel engine. And the last problem identified includes Karanja biodiesel has a great improvement in performance. And the results of this B20 or the Karanja diesel is that maximum production efficiency is attained at B20 biodiesel. And B20 biodiesel blend is having the better compression characteristic in spite of the differences with respect to the fatty acid composition, physical properties, and chemical properties. And there are some methodology used which also includes RSM, which is nothing but resonance surface methodology for the optimization technique and also for the experiments where the best optimization was done and the results are being considered accordingly. These are some of the gaps that is been identified from the literature. Air intake manifold design needs to be improved. Proper material is not chosen for air intake manifold. Plastic material are not attempted by many for air intake manifold. Alternate fuels are not studied for plastic air intake manifold. Modeling and analysis of air intake manifold is not done properly. Models of response parameters for various air intake manifold for diesel and biodiesel are not available. And these are the objectives and methodologies of the research. The objectives of the research involves assessment of an optimal air intake manifold design tailored for single-cylinder engines with a focus on enhancing performance. Comparative analysis between plastic and aluminum as potential material for air intake manifold construction, considering their impact on engine efficiency. Fabrication and experimental testing of diesel engines equipped with various air intake manifold designs and materials to assess their performance in connection with both the diesel and the biodiesel or alternate fuels. Modeling and optimization of the parameters based on the outcomes of the experimental testing aiming to identify the most favorable engine configurations and settings. And these are all the methodology of my research. Proposed intake manifold designs and manifold materials for a single cylinder diesel engine. Then testing and analysis with proposed manifold designs with diesel for single cylinder diesel engine. Modeling and optimization of engine parameters with proposed manifold designs with diesel for single cylinder engine. Testing and analysis of optimized manifold for proposed manifold materials with diesel and biodiesel for single cylinder engine, testing and analysis with both manifold materials for diesel and biodiesel in multi-cylinder diesel engine, modeling and optimization of engine parameters with the proposed uh, manifold materials for diesel and biodiesel in multi-cylinder engine. And finally, I'm comparing the results of manifold material on singles and multi-cylinder engines. So these are the materials and methods. The specifications of the single cylinder engine is basically it's a vertical engine having a four-stroke cycle, single acting, totally closed, high-speed compression, single cylinder diesel engine, and the bore is 87.5 mm, the stroke is 110 mm, the cubic capacity is 661.5 cc, and the compression ratio is going to be 17.1:1. The power is 3.5 kilowatt power at 1000 RPM, and cooling method is air. And this is the setup of the single cylinder engine. And coming back to the specification of multi-cylinder engine, it's a four-cylinder inline four-stroke cycle compression and ignition multi-cylinder diesel engine having the bore of 85 mm and stroke of 96 mm, and the cubic capacity is 2179 cc, and the compression ratio is 16.5:1, and aspiration is turbocharger, and the power is 103 kilowatt at 3750 RPM, and the method of cooling is water. And this is the layout of the configuration of multi-cylinder diesel engine. These are all the proposed manifold designs for a single cylinder engine. This is the design 1 manifold, this is the design 2 manifold, and design 3 manifold, and this is the design 4 manifold. And the proposed design of the single cylinder manifold, what I have shown in the previous slide, it is going to have the greater fuel trap inside the cylinder, which will result in the high maximum kinetic energy. And as I told you, there are four designs: design 1, design 2, design 3, design 4. Initial material what uses aluminum, and the swirl ratio for the design 1 is 0.75, 1.2 for design 2, and 2.16 for design 3, and 0.8 for design 4. And the runner length in inches is 10 inch for design 1 manifold, 14 inch for design 2 manifold, 12 inch for the design 3 manifold, and 10 inch for design 4 manifold. And the runner diameter is 1.75 inch for design 1 manifold, and 1.2 inch for design 2 manifold, and 1.5 inch for design 3 manifold, and 1.3 inch for design 4 manifold. And these are the specifications for all the four manifold designs. Proposed air intake manifold materials for a single and multi-cylinder engine. So we have PS6 with the glass fiber 30% and PA66 with glass fiber 13% glass fiber. And the benefits of PA66 when compared to that of PA6 is it is having the absorbing capacity marginally less moisture. It also has PSC66 is having greater modulus, the sound wear resistance, and also it has short-term heat resistance when compared to the top PA6 glass fiber of 30. And when you're comparing PA6 with PA66, PA6 is better for ductility because of its high toughness, and PS6 is also having the high long-term heat resistance, and PA is when compared to the PA66 glass fiber 30, and PS6 is also superior, having the superior impact resistance in small temperatures, good surface quality, and improved creep resistance, and better UV resistance, and also the cost is also lesser when compared to the top PA66 with glass fiber of 30%. And this is a material comparison between PA6 glass fiber 30, PA66 glass fiber 30%, and aluminum silicon copper Cu3 material. You can find that the tensile strength is higher in the case of PA6 with glass fiber 30 when compared to the top PA66 glass fiber 30, and also the aluminum silicon grade material. And you can also see that the thermal conductivity is less in the case of PA6 glass fiber 30 when compared to the top PA66 and also aluminum silicon. And the very important aspect here is the density is lesser in the case of PA6 with glass fiber 30 when compared to top PA66 and also the aluminum material. And the melting point of PA6 is 260 degrees Celsius, whereas PA66 with glass fiber 30% melting point is 250 degrees Celsius, and aluminum grade is 660 degrees Celsius. And this is the injection molding process. The composite materials are the products which are made up of distinct physical states, which one being in the fiber state, while other being in the form of distributed, which is in a matrix form. This in the first stage, the polymer matrix is pre-mixed, where the polyamide PA6 with glass fiber of 30% are been mixed, and the reinforcement of PA6 with glass fiber of with glass fiber or 30% are been carried out. Next, the raw material with PA6 glass fiber 30 are been stored, and the PA6 glass fiber 30 materials are been taken inside the collector of the injection molding machine. This is the machine, injection molding machine, where through the hooper the material are been poured inside, and the materials are melted and passed through the hot runner, and when it comes out, uh, the shape is been updated, and the mold closing time is going to be for 1 minute, and after that the mold opens, and after that the material filled to get the required shape of the air intake manifold, and then finally the PA6 with the glass fiber 30% air intake manifold are ejected out from the injection molding machine. And same process is also been followed for PA66 with glass fiber 30% as well. And this is the development of the single cylinder PA6 glass fiber 30 and also PA66 glass fiber 30, and this is the multi-cylinder engine having the material PA6 and PA66 glass fiber 30%. And this is the trans-esterification process, which is how this is how the biodiesel has been manufactured. First is that the vegetable oil, which is nothing but a karanja oil we have used for my research, is taken in a flask, and methanol and then catalyst are been mixed together, uh, and then the NOH is mixed with alcohol and until it gets dissolved, and then the solutions for this process have been mixed together, and where uh, the stirrer has been used to mix, and the solution is been made where we have also have a separate beaker, and we are adding the glycerin as well. And finally, what happens? You see here first the methanol catalyst, and this is the karanja oil. First, you are going for a pre-treatment, then doing that, you are going for a separation of the trans-esterification process where the glycerin gets separated, and also biodiesel gets separated. And here during this process, what you do is you are also washing and also drying the thing. Finally, the biodiesel which is going to come is not going to have any contamination. It is going to be an uncontaminated karanja oil, and which is having the better emission and combustion assessment for the performance. And this is the property of diesel karanja oil B100 pure biodiesel, and biodiesel P20, where 20% is karanja oil and 80% is diesel. And you can see that the kinematic viscosity is 4.3 for diesel and 4.84 for karanja blend P20 grade. And you can also see that calorific value is also nearing between B20 and also diesel fuel, and the density is also almost close when compared to the top pure B100 Karanja biodiesel. So this is the reason why we are going for B20, as these properties are nearing to the term for diesel. This is the RSM technology or RSM process, resonance, RSM stands for resonance surface methodology. So here, Y is nothing but f of x, where Y is nothing but the resonance, and x is nothing but the input variables. So we give the input x1, x2, x3, x4, up to xn, and we get the response called y. And if the factors are known, then we are going to estimate the effects and interaction of the model. And if the factors are unknown, then we are going to calculate a screening method. And we are also going to estimate the interaction effect by using the first order model, where y is nothing but the response, which is nothing but beta 0 plus beta 1 x1 plus beta 2 x2 plus all plus psi. So if curvature is found, then we are using then we are going to use the RSM technique, and we are going to make a graph to find the stationary point, maximum response, minimum response, and saddle point by obtaining the values of uh, the input variable, which is x1, x2, x3, and x up to still x9. And we are also going to use the desirability approach, where we are going to give a range between low to high, and then this low to high is being given for the various parameters like BSFC, breakdown efficiency, emissions, COHC, NOx, unburned hydrocarbon, and also for the volumetric efficiency, airflow rate. For all this, we are going to give input range and also our maximum range, ranging between low to the maximum. And this is the experimental setup. Next is going to be the experimental setup and testing procedure. This is a single cylinder engine which is placed on the engine bed. This is the water in and we have water out. And all these four designs manifold are being put into this, and they have been tested for the various performance emission characteristics using diesel and biodiesel. And this setup is going to be the eddy current dynamometer, having the dyno controller, and it's also having the tank, diesel tank, and fuel consumption measurement also be taken. This is a testing procedure for a single cylinder engine, where first the engine is fitted with a design on manifold and readings are taken for diesel fuel. Fuel consumptions and emission values are noted, and the manifold is changed into design 2, design 3, and design 4 manifold one by one, and the readings are taken again for the diesel fuel. After optimizing the design, the readings are taken again with various manifold materials for diesel and biodiesel fuels. Next is the experimental setup for a multi-cylinder engine. This is the multi-cylinder engine setup. It is similar to the single cylinder. And here we are going to use three different manifold material: PA6 glass fiber 30, PA66 glass fiber 30, and aluminum silicon 8, copper 3. Three grade of materials we are going to use, and we are going to test the proposed design along with these three materials in the multi-cylinder diesel engine. This is the testing procedure for a multi-cylinder engine. Engine initially is fitted with aluminum manifold, and the readings are taken for diesel and biodiesel. The fuel consumption and emission values are noted. The manifold is changed into PA6 glass fiber 30, then PA66 glass fiber 30 manifold one by one, and the readings are taken again for diesel and biodiesel fuels. And let us go to the results and discussion. Results of analyzing air intake manifold with different manifold designs for a single cylinder. This is the graph showing the SFC versus flow. You can see that BSFC for design 1 manifold is lesser, which means it is better than other design. It is because of the better spill incoming air for design 1 air intake manifold. and the fuel consumption is also reduced with design 2 manifold when compared to that of design 2, design 3, and design 4. The fuel consumption is much better, which means the SOC is better, lesser, which means it is better uh, because of the better airflow. There is no airflow restrictions, and also there is no back pressure in the case of Design 1 manifold. But those restrictions and the airflow and back pressure restrictions are there in the case of Design 2, Design 3, and Design 4 manifold. That is the reason SFC of Design 1 manifold is lesser. Coming back to the second parameters, BT versus load, you can see again the brake terminal efficiency is higher for Design 1 manifold when compared to that of 2, 3, and 4. And the reason behind here is the maximum BT is achieved for Design 1 because of the effective design, and it is not affecting the combustion as well. And when you're comparing the Design 4 with Design 1, Design 4 is almost 6 percentage lesser bed thermal efficiency when compared to that of uh, Design 1 at the full load. There, this full load, you can see almost 6 percentage bed thermal efficiency is higher for Design 1. This is the next graph, which is CO versus load. In this CO versus load, the CO is lesser for Design 1 manifold when compared to that of Design 2, Design 3, and Design 4. This is because the Design 1 air intake manifold does not affect the compression. And also the airflow inside the manifold also having a better spill. And as a result of that, it is having a better mixing of air and fuel and enhances the good greenhouse effect combustion. You can see here the Design 4 is almost having 27 percentage higher CO emission when compared to that of Design 1 manifold at full load. Basically, at this full load, you can see almost 27 percentage higher CO when comparing with Design 1 versus Design 4. Design 4 is 27 percentage higher CO emission. Next is CO2 versus load. And here also you can find that Design 1 having less CO2 in compared to Design 2, Design 2, and Design 3, and Design 4. And the reason behind here is Design 1 is not affecting the combustion. And also the airflow inside the cylinder is also having a better spill. And you can see at high load, at full load, Design 4 is almost 6 to 7 percentage higher CO2 when compared to Design 1 manifold. And next is going to be the graph having the hydrocarbon versus load. And here also it is obvious that H is lesser for Design 1 manifold when compared to that of Design 2, Design 3, and Design 4. And the reason here is increased airflow restriction within the combustion chamber, leading to the inadequate air fuel mixing during combustion, thereby causing incomplete combustion. The onboard hydrocarbon emissions are minimal for Design 1 manifold, while they reach the peak for this Design 4. You can see the peak here, and you can see almost 66 percentage. You can see it is having higher onboard hydrocarbon for Design 4 when compared to the of Design 1. Next is NOx versus load. Again, in NOx in the case of NOx versus load, the findings illustrate that NOx emissions were lower for Design 1 manifold, which primarily attributed to a reduced ignition delay period and improved fuel mixing. And design two air intake manifold almost you can see that design 2 is almost similar and it's also closer to design 1 manifold, and design 4 is having the high knocks when compared to the rough you can see the high knocks is there for design 1, and the reason for this high knocks it is because of high exhaust gas temperature, and design 4 is almost 18 percentage higher than design 1 manifold yeah, at 100 percentage load at full load condition. And next is the smoke versus load. You can see that um, design 1 is having high smoke when compared to the of design 2, design 3, and design 4, and almost design design 4 is having 11 percentage less smoke when compared to the of design 1 manifold. And, next is the modeling and optimization for single cylinder with various manifold designs. We done the experimental design matrix, and we have used various input parameters which involves load and manifold designs, and response parameters involves BSFC, BT, hydrocarbon, CO, CO2, unput hydrocarbon, NOx, smoke, and we used design software, design expert software called StateEase, which is a US-based software, and we have done almost 51 experimental runs. And modeling and optimization for single cylinder with various manifold design and the criteria for optimization. And we have used various parameters and the lower limit and also upper limit for load 0 to 3.5, and we have used order 4 designs. And we have the limit for BSFC, BTE, CO, CO2, HC, NOx, and smoke. And we have the lower limit, lower weight as 1 and upper weight as 1, and importance is high, so that's why we are putting as 3. And based on this, we got a solution. We got a 5 best solution. Top 2 is for design 1, and the next 3 is for design 3. And we have selected the best design based on SFC, PTE, CO, CO2, HC, NOx, and smoke, and also based on the disability factor. Higher disability factor, I have selected that as the best design. So design 1 is the best design out of the design 1, design 2, design 3, and design 4, based on the various parameters that have been optimized. And the results of analyzing single cylinder engine with optimized manifold design for various multiple materials with diesel and biodiesels. So here what I have done is I've taken diesel and also biodiesel as a fuel, and I have analyzed the performance and emissions of PA6 and glass fiber 30, and also PA66 with glass fiber 30 and aluminum material. So the findings here reveal that the PSFC for PA6 with glass fiber 30 is comparatively less when compared to that of the other PA66 and also aluminum. And this is because of the material property of the air intake manifold, which is causing the incoming air to get an increase in density. The improvement in air density resulted in enhanced air fuel mixing during compression. The fuel consumption is lowered for biodiesel blend. You can see the biodiesel blend is having the lesser fuel consumption because of the lower calorific value. Whereas for aluminum and PA66 air intake manifold, the fuel consumption is also observed closer to that of the diesel. You can see the graph. And next is going to be the brake thermal efficiency versus load. And here you can see that the PS6 with glass fiber of 30 is having the high brake thermal efficiency when compared to the PA66 and also aluminum. This is because of the incoming air and also the high increase in the density. The enhancement in the air intensity results in the improved air fuel mixing during the combustion. And the graph highlights that the manifold material plays a vital role, crucial role in influencing the drug thermal efficiency. And PA66 glass fiber of 30 materials is showing the improved drug thermal efficiency for both diesel and also the biodiesel. Next is CO versus load. You can see here the biodiesel CO is lesser when compared to that of diesel, and also you can see that also you can see that the manifold design promotes the enhanced airflow automation during combustion, which is reducing the oxygen deficiency in the process. And the PA6 material is also having the low CO emissions. The PA6 is having the low emissions when compared to the top PA66. And this is CO2 versus load. You can see here diesel is having the less CO2 when compared to top biodiesel. And the biodiesel with aluminum and biodiesel with PA6 are almost closer values when compared to that of PA66 with glass fiber of 30. And you can also find that by employing aluminum and the PA6 glass fiber, it is leading to a substantial of 70% decrease in CO2 emissions. And next is going to be the unburned hydrocarbon versus load. As far as the unburned hydrocarbon versus load is concerned, biodiesel is having the less unburned hydrocarbon compared to raw diesel. And here also you can find that PA6 is better than raw PA66. And even you can also find that the HC emissions was notably low for PA6 when compared to the PA66 because of the material property, which causes the incoming air to get an increase in density, and the air density which is facilitating the higher improving your air fuel combustion mixer. And the manifold design promotes the better optimization of air flow during combustion, which is leading to the complete combustion and also the reduced HC emissions. Next is going to be NOx versus load. In this NOx versus load, you can find that diesel NOx is lesser when compared to the biodiesel, and even in this case as well, PS6 glass fiber is better than the top diesel with biodiesel. And in the case of NOx versus load, the fabricated three materials were fueled with diesel, and it is exhibiting lower NOx. And you can also find that the decreased the ignition delay period and improved combustion contribute to the higher NOx. The improved air density is facilitating the better mixing of air fuel during combustion. The manifold material design also promotes the superior atomization of airflow during combustion, which is leading to the incomplete combustion. And next is going to be the smoke versus load. You can find that Air Intake Manifold with these three materials, when it is fueled with the diesel and biodiesel, it is exhibiting the lower smoke emissions. This reduction is because of the decreased ignition delay period and also the improved combustion. And the higher air density facilitated improved the high mixing of air fuel during combustion. The design of the manifold enhances the atomization of the airflow during combustion. And the smoke, as far as smoke is concerned, it is less for biodiesel when compared to that of the diesel. And this is the modeling and optimization technique for a single cylinder engine with optimized manifold design for diesel and biodiesel. And the criteria for optimization, and here also we have used the different parameters like load, manifold type, fuel, SFC, ductile efficiency, CO, CO2, HC, NOx, smoke. And we have put a lower limit and higher limit, and lower weight is one and upper weight is one, and the importance is high. And we have used the load between 0 to 3.5 and aluminum material PA6, PA66, all the three manifold are being considered in both diesel and also in biodiesel, and these are the different ranges for the different parameters. And this is the solution for optimization, where we have found that PA6 with glass over 30 biodiesel blend is better with respect to the SFC, BTE, CO, CO2, HC, NOx, smoke. And considering all these parameters, we get higher disability factor for PA6 with glass over 30%. And the last part here is analyzing the air intake manifold with different material for multi-cylinder engine. You can see here power versus speed. Power versus speed for biodiesel is lower when compared to that of diesel. And the maximum rise in power is for D plus biodiesel, D plus diesel with PA6 glass over 30. You can find that the maximum power is been achieved when at up to 2250 RPM. You can find that this 2250 RPM, the maximum power has been achieved. And this maximum increase in power of almost 9% is obtained when compared to the top PA66 at 4000 RPM. And next is torque versus speed. You can see that the torque is also higher for D plus PA6 glass fiber of 30 when compared to the top PA66. BSFC versus speed, we get less fuel consumption for PA6 with glass fiber 30 because of the complete combustion. And volumetric efficiency also, you can find that it is high for diesel plus PA6 of glass fiber 30. And this is the airflow rate. And the airflow rate is also high for diesel with PA6 glass fiber 30, and also in biodiesel also PA6 with glass fiber 30 is having higher airflow rate when compared to that of biodiesel. Sorry, when compared to that of other materials, PA66 glass fiber 30 and aluminum material at various speeds. CO versus speed, carbon monoxide is lower for diesel with PA6 compared to the PA66. And finally, CO2 is higher for aluminum and followed by PA6 and lastly PA66 for both diesel and biodiesel blend. And speed versus NOx, we can find that because of height, increased exhaust gas temperature for this PA6 glass fiber 30, it is having a higher NOx at various speed, and followed by which PA66 is coming second, and lastly aluminum grade. And smoke is higher in the case of PA66 glass fiber 30, since the NOx is less there, smoke is opposite. And this is the pressure versus crank angle. You can find that diesel with PA6 glass fiber 30 air intake manifold results in the high peak pressure during combustion, and this is because of the improvement in the air density with respect to the air intake manifold during combustion. In the case of biodiesel with aluminum and also with PA6 or glass fiber, air intake manifold peak pressure is slightly higher, and this is because of the reduced ignition delay period and the use of PA6 air intake manifold contributing to the improved mixing of fuel air ratio and enhance the combustion performance. Next is see cumulative heat release rate versus crank angle. And in this case, we can find that diesel with aluminum is having the high CHRR when compared to that of PA6 and PA66. And diesel with PA6 glass fiber contributing to the maximum heat release during combustion, and it is because of the improvement in the density with respect to the air intake manifold during combustion with respect to biodiesel of PA6 one. The heat release is completely marginal, okay? And the observed effect is credited to the increased emission delay period, which is affecting the homogenization of the air fuel mixture, and it is enhancing the better combustion and performance. Next is the results of modeling optimization of engine parameters for multi-cylinder engine with various manifold materials for diesel and biodiesel. These are all the experimental design matrix where input parameters are the speed, manifold materials, and fuel, and response parameters include power, torque, base efficiency, blood efficiency, volume efficiency, air fuel ratio, HC, CO, CO2, unburned hydrocarbon, NOx, and smoke. And we used the design expert version 13 software of Statis, and we have done 51 experimental runs. And this is the criteria for optimization. Different criteria, different goals is it's in the range. Say for example, speed is between 1000 to 4000, and the material range is all the four materials. Diesel for both diesel and also biodiesel, and power, torque, VSFC. There's a limit for all the things, and we have the lower weight and the upper weight and importance, which are considered as the high value. And this is a solution, and based on the solution, what we got is we got diesel with the PA6 class over 30% is better design comparing to the other combinations, and the disability factor is also higher. And this is the comparison of single cylinder multi-cylinder diesel engine for air intake manifold material modification. And these are all the parameters, PSFC. So when you're taking PSFC, the average increase or decrease in maximum value for PA66 class over 30 when compared to the of aluminum for a single cylinder diesel engine is minus 2.80%. Similarly, it is minus 8.63% for PS6 glass fiber 30 when compared to the aluminum. And this is for a single cylinder engine. For a multiple cylinder engine, it is minus 0.556 and minus 11.64 in the case of PSFC. And you can also see that blood thermal efficiency is almost 2.91 times higher when you are going with when you are comparing the aluminum with PA66. But when you are comparing the PA6 with aluminum for a single cylinder engine, you can also find that maximum you can get 8.52 blood thermal efficiencies on the higher side. And the average increase or decrease in the maximum value for PA66 when you are comparing with aluminum for a multi-cylinder diesel engine is going to be 3 and 9.49 in the case of blood thermal efficiency becoming comparing the PA6 with aluminum. And these are other comparisons: CO, CO2, unburned hydrocarbon, NOx, and smoke. This is for diesel, and the next one is for the biodiesel. Finally, conclusion here is the Diesel and Manifold shows a better performance in a single-cylinder engine with diesel and biodiesel. A multi-cylinder engine is modified with to Diesel 1 and analyzed. The manifold materials are changed and tested with diesel and biodiesel. This shows that the design of plastic intake manifold with plastic PA6 with glass fiber 30% is better design for the pressure drop across various cylinders. Diesel plus PA66 material glass fiber 30 material properties are comparable with diesel plus aluminum silicon copper by adding glass fiber with plastic grades. And the performance of an engine where three different intake manifold with different materials for D plus PA66 glass fiber 30 and D plus PA6 glass fiber 30 and D plus aluminum silicon copper are compared. The result shows that diesel plus PA6 is having better high drag power, high torque, high volumetric efficiency, and airflow rate when compared to that of aluminum and diesel plus aluminum at all speeds. Also, D plus PA6 with glass fiber 30 results in a reduction in VSFC when compared to that of D plus aluminum silicon copper and D plus PA66 glass fiber 30. The high specific heat of diesel plus PA6 glass fiber 30 results in reduction in temperature inside the air intake manifold, which increases the volumetric efficiency. Diesel plus PA6 glass fiber also shows a slight increase in engine performance when compared to the top diesel plus aluminum silicon grade. So these are my future work. The air intake manifold can also be tested for other biodiesel blends apart from Karanja. The air intake manifold can be tested for gaseous fuels like LPG, CNG, etc. The air intake manifold can be manufactured for nanomaterials mixed with plastic for improved strength. These are my four list of obligations. Some of which involves the Journal of Thermal Analysis and Calorimeter and the diagram of hypothesis effects of air intake manifold design, investigation of diesel engine parameters on different alternative fuels. And second, this is probably involves significance of intake manifold material and engine performance. And third paper is development of air intake manifold using alternate materials by CFD. Lastly, thermal durability analysis of PA6 glass fiber 30 and PA66 glass fiber 30 air intake manifold. And these are also some of the references. I will taken more than 100 references, which have been quoted here.